Hey, everybody, welcome back to your Dawn of Autonomy podcast. I'm Dawn Zoda, your host and the CEO of P3 Tech Consulting. We are in a month that we've dedicated to this theme of dual use technologies, sponsored by Fixar. But today we have on the show as our special guest, Mario Paniccia from Anello. Yes, and we're going to be talking about this interesting thing that he and his team have created called the Sci-Fog, and we're going to get deep into this thing called Photonics, and you're going to be like, what? And then after you hear it, you're going to be like, I need one of those on my vehicle. So let's go ahead and get started, Mario. So great to have you on the show.
Sure. Thanks, Don, for inviting me, and thanks for hosting us, and really excited to tell you more about Anello.
Absolutely. So, by the way, guys, everybody out there, fun fact, I met Mario this year in January at CES in Las Vegas. Anello had a booth, and they were unveiling their X3, which we're going to talk about today. And that's the first time we chatted, and wrote an article for Inside GNSS Magazine about the X3. So we'll drop that link for you. But before we get to all the cool things you're doing, Mario, let's talk about you first. So tell us a little bit about your background.
So I spent 22 years at Intel Corporation. I was an Intel Fellow, which at that time was the senior technical level of the company. At that time, I developed an area which now is called silicon photonics, which was the idea of building optical devices out of using the standard silicon processing that we use for integrated circuits. So the idea of bringing light in to silicon, manipulating it, transmitting it, and so communicating between chips using standard CMOS silicon processing. Took that technology to commercialization. I think I was one of the few Intel fellows that actually ran a business unit. But it was really focused on high-speed interconnects at that time for the data center. If you go back, it seems, 10 years ago, the idea of video and YouTube and that stuff was just coming, and the bandwidth demands across the data centers that you couldn't push copper very far. So the idea between chips or servers and racks with fiber, but as that demand increased, we needed to drive the cost down. And the idea was to use this silicon photonics technology. If you fast forward, probably 50% of the data centers around the world are based on integrated silicon photonics technology.
Okay, wow, head exploding. So let's walk it back for people that might not know what photonics even means. Okay. Tell us, at the, let's say, high school level, what photonics means.
Okay, there's two types of ways to transmit data. One is through electrons. So you have a copper wire and you can send data from point A to point B, and you send an electrical pulse, and that's through electrons. The other way is through photons, and that you have an optical fiber. You can think of a laser pointer or a laser beam sending data with lasers. And the benefit of that is photons have no mass. They don't interact. And so you can transmit photons very far and at high speeds. The problem with transmitting with photons is it's expensive. And so again, electron, everywhere you go today, any kind of cable you have, USB cable, is transmitted electronically. And as you go to higher data rates, right, today, in your Wi-Fi at home, it's a couple hundred megabits. Over fiber, you can get to hundreds of gigabits per second. And so the idea of transmitting things very far and very fast leads to a fiber optic-based solution where you want to transmit data with photons. To counteract the cost of that is how do you build devices that are cheap? And that's using this world economic thing called silicon, right? That everything's produced through silicon factories and silicon fabrication facilities. And so we created the idea that I can take silicon and use that to manipulate and transmit data using photons.
Wow. Okay. I can actually understand that. So kudos to you. And so So is this kind of, have we already started getting into the origin story then of Anello? Because, you saw this problem out there and thought, hey, there's a lot of different multi-domain vehicles that are going to need to go beyond visual line of sight. They're going to need this kind of technology, and we're going to be the ones to make it. Tell us about that story.
Yeah, so if you take about the silicon photonics revolution, it was about 20 years in the making. I gave a talk recently on the 20th anniversary. And when you bring a new technology to the industry, it's typically about 10 years to develop it, 10 years to commercialize it. And I would argue today in the data center for transmitting data, it's 800 gigabits, 1.6 terabits, 3.6 terabit. The bandwidth demands in the data center are insatiable. But then people started saying, hey, I have this integrated photonics. Think of this just like the vacuum tube transition to the integrated circuit. I could take these big bulky things, put them onto a small chip, and I could do new things. So LiDAR evolved. People started putting integrated photonics to apply it to LiDAR for applications in autonomy for viewing things. And a friend of mine who's a VC introduced me to our co-founder, Mike Horton, who's a sensor guy. And he was doing MEMS for a long time. And he said he wanted to build an optical gyro because the accuracy needed for autonomy, the MEMS just can't get there. I'll talk more about it later. So Mike and I met, and he said, I want to build this optical gyro. And to be honest, I said, what's a gyro? Because I never,
You just asked the question that I was going to ask you. What is a gyro?
I'll explain in a minute. And I said, to be honest, the first thing that went to my head was, is it chicken or beef? So we started talking, and I said, we could build that. And he said, no, you don't understand. I said, no, we could build that. It's based on integrated photonics, but it was a new application of taking those same components and applying it to a new field. And that was the formation of Anello. And then I'll talk more about the gyro. But if you understand what Anello is, and the word means ring in Italian. And I know you have some
It means
Italian
ring?
heritage. It means ring. So Anello is ring in Italian. Anello, right? And so the question is, what's a gyro, and then how does this revolve to Anello, what we're doing here?
Yeah.
So gyros measure position or drift, right?
Okay.
And that everyone knows there's a common gyro here, right? There's a gyro in your phone, there's a gyro in your earpod, in your watch, and when you turn it, it measures the rotation and it turns on your phone, or it turns on your earpod or your watch. And those are based on MEMS, micro machine, the electronic machine, they're pieces of silicon. They're billions of units a year, right? They're billions of phones sold. They're very cheap, right? Billions of units. It's basically a floating membrane that's capacitor. And as you move it, the frequency of that membrane changes, and you can use that to measure rotation.
Okay.
So it works fine. The drawback is it's not very accurate. And so for autonomy, and you want accuracy, MEMS has a couple faults. It's basically very sensitive to temperature. It's very sensitive to vibration. So if you're moving on a car and you go over a bunch of rocks, it's basically throws it off.
Or you're just flying a drone through the air.
Yeah, and so anything that moves or wings or vibration. And it's also very sensitive to EMI, electromagnetic interference, because it's basically a capacitor. So while MEMS are out there, for high precision accuracy, what's typically done in the industry is called fiber optic gyros or ring laser gyros. And those are based on what we talked about earlier, based on photons. So you have a laser that goes around, it gets very simple. A fiber optic gyro has a laser coming in, splits into two beams, so I can explain this, and you have a coil. And the light goes in that coil in two different directions.
Okay.
As that coil rotates, the light going in the same direction as the rotation goes a shorter distance than the light going the opposite.
Okay.
So the visual for those here listening are, just think if you're at the airport on an escalator and the escalator is moving. Yep. If I stand still, I go at one pace. If I walk in the same direction as the escalator, I'm going to go a shorter distance than going the opposite.
Yeah.
When those two propagating beams combine, they interfere. And if you remember, when you interfere two sine waves, it's the beams of light, there's a phase difference. as those sine waves interfere.
Okay.
And that phase difference is proportional with a lot of math to the rotation rate.
Okay.
So if you build a system that can measure this tiny phase signal, you can accurately measure the rotation. That's what a fiber optic gyro does.
And I imagine in a highly accurate manner.
Yeah, to put it into context, we're measuring about 50 nanoradians of phase. So that's 10 to the minus 9. Very, very tiny. Because remember, this is the speed of light going around the coil, but it's very accurate. If you build an interferometer and electronics, you can pull that tiny, tiny signal out. So what we did was we said, hey, this is a typical fiber optic gyro, right? This is a 3D print of an LN200. It's the main steam. It's in every ICBM and every fighter jet. This has been around for 30 years.
Okay.
But you see the size of this, right?
Yeah. Can you put it up against your palm just for better context?
Yeah. So it's like I say coffee can size, but a lot of people don't know what coffee can is anymore. So this is 4 inches high, 5 inches, 4 inches in diameter, 5 inches high.
Okay, gotcha.
But this gets you the sense of a coffee can size, and I'll show you what we built.
And you slipped something in there, Mario. I want to highlight because you just ICBMs, fighter jets. These are the kinds of high precision vehicles that are using this technology.
Yeah, so if you look at gyros, there's two things. I'll call it industrial grade or consumer grade, which is MEMS based. Yep. And then there's strategic or navigation grade. So this is fighter jets. If you go really low, submarines. Okay. If you go underwater, and some of those submarines are six months underwater, those are
oh wow.
If you want higher performance, you go bigger.
Okay.
And so we started saying, hey, if this is a discussion with Mike and I, when you look at the autonomy market, people want better performance. If you want accuracy, if you want to drive down the road and you lose your GPS, so you go into a tunnel or you go into urban canyons, you need to be able to pull over to the side of the road. You need to know where you accurately are within a few seconds. And that leads to performance metrics that are better than 0.5 degree per hour, if you look at the terms of performance. So we said, hey, MEMS are running out of steam. They physically can't get to below 0.5 degree per hour. Or if they're at a 1 degree per hour, over temperature, they're hundreds of degrees per hour. So they're not very good for accuracy. The fiber gyro world, or ring laser gyros, while they're very accurate, they're just not going to get to the price points. You're not going to take a $40,000 box. Yeah. I say shave the gold off it, and now it becomes cheap.
Well, plus it's too big.
It's big, bulky. It's called size, weight, area, power. All 4 of those. So we said, if we do a radical new way, what if we take the concept of silicon photonics, take the physics of a fiber optic gyro, but take the same concept and put it onto a silicon chip, and put all those components and build an optical fiber optic gyro based on silicon photonics. If we could do that, that was the premise of Anello when we started, we can build a small, low-cost, scalable device or sensor that's high precision, low power, but that can be scaled to the mass market. And that was the premise of Anello when we started, right?
Now, when did you start? What year are we talking about?
So we officially started, both Mike and I were obviously running other companies, and we decided to start this. We wound those companies down right around 2019 and early 2020. And if everyone remembers those dates, it was the premise of COVID. Yes. And, it's not the best time in the world to start a new company. Nope. Everything was shut down.
Although I did the same thing, Mario. My timeline tracks yours exactly.
Okay. So, it was 4 of us, the 4 or 5 of us, the founders, and a few of us, and we had no choice. We came into work, but it was really hard to get stuff done. Luckily, we spent a lot of time on the modeling and simulation. We filed an enormous amount of IP, and then things slowly started to pick up. And just to go back to, I keep talking about fiber optic gyro. Yep. Where does SciFog come from? It's not SIPHOG, it's SciFog.
SciFog.
SciFog, Silicon Photonics Optical Gyro. So it's a spoof off of fiber optic gyro. Yeah. And that was so step forward. this concept and we say, okay, we want to build these optical devices. Now, remember, silicon photonics is being used in the data center for high-speed connectivity, right? It's high volume today, and volume today in the data center, we're talking tens of millions of units, okay?
Yep.
The problem with building a fiber optic gyro or SiFog is completely different. There were no models, there were no tools, so we had to build our optical test chips, and we had to start the simulations from scratch. We had to build our own devices, and it's painful because you put a test chip in the factory, in the silicon fab, you wait 3 or 4 months to get it back, you test it, oh, that wasn't correct, retweak the model, and come back. And so it took us a few years to build the SiFog, which I'm happy to say, here it is. This is the SiFog, right?
So this is tiny. All right, this is a great
you put it in the palm of your hand. It's a basic fiber optic gyro.
It's
do
like
little card tricks.
Is it like a little bigger than a postage stamp in a way?
Yeah, it's about a sub an inch square, but this is you see SiFog.
Sweet. Now
what's in
I
here?
think we also might have an image of that we can pop up as well as we're talking.
Perfect.
Here
there
we go.
Is.
All right, so
go fast forward. So what's in here? What we've done is we've taken all these big bulky components, fibers, modulators, lasers, detectors, and we put it all into a silicon photonic integrated circuit we call PIC. Understand that PIC is tiny. It's roughly 2 millimeters by 5 millimeters. So I've taken this tabletop stuff of equipment and I put it all into a little chip, and every little device is manipulated, no reflections. You're building a fancy interferometer, so any back reflections, any light that's scattered affects your signal. Then we also built a bunch of electronics, and this is a very complicated circuit, and we always talk about the photonic piece, but this is the electronics that's in there. It's a double-sided, full analog lock-in temperature controller, laser controller.
Yeah.
And now what results from this is the SiFog. Now, what's so exciting about this? This is low power, first of all, 3.3 volts. You can mount it on a board.
So it's not sucking battery.
It's not sucking a lot of power. It's not susceptible to temperature. It's not susceptible to vibration because it's photons, right? So, photons don't interact with things. And lastly, it can be scaled in high volume because it's made based on pick and place technology. While there's a laser and a sub-assembly here, and we have a small pilot line here in California. So now you have this radical new thing, this concept that was only for the high end.
Yeah.
That was, I'll call it military grade, high performance. Yeah. I've now created something that is small with high performance that can be scaled to high volume.
So, Mario, when did you launch this? Like, what year did this, the original SiFog you're showing us, when did that come out?
We officially launched SiFog in 2023. Also at CES, we've turned out that CES, which is the Consumer Electronics Show in Las Vegas where we met, turns out to be a great place to launch our new products because, remember this, and we'll tie later on about the dual use.
Yeah.
While this predominantly was for high-end applications, we're seeing dual use applications because, again, we're trying to build this technology for the high volume.
Yeah.
And so now you have SiFog, this concept that I've just created, high performance.
Yep.
Capability, or with a gyro drift, very low performance, low accuracy, that predominantly was only at the high end. So now for the autonomy market, let's talk about the use cases.
Yeah, please.
Whether it's industrial. Well, let me talk to you. So first of all, we have SiFog. And this we launched last year at September 2023. Now, while this is this is the first new gyro in 20 years. What do you do with it? And we don't sell SiFog, at least not today. We take the SiFog, and this leads to how we put it into systems. And then we'll talk about it. So this is an example of if I take the SiFog or optical gyro, and this is what we call our GNSS INS unit.
Okay. So global navigation, satellite systems, inertial measurement.
Which is GPS, inertial navigation system. So I now put this into a system. There you go. And now let's say for land vehicles. So for land vehicles, as you're driving, the heading is the key parameter. So 95% of the performance is the heading. While you're moving around the road, your wheels are still stuck to the road. So it's not really a three-dimensional problem.
Okay.
Now, what I also don't tell you, inside this SiFog, we also put other things in here. We put accelerometers in here. We put triple axis MEMS gyros for course alignment. We have temperature sensors. There's a lot of other stuff in here that read out information. I now put this into a box or a system. There's two antennas.
Okay.
This isn't a sealed unit. So this is salt spray. You can throw this in a pool, IP68. But now you have this high precision optical gyro capability. So now I'm driving, and now this is where you now combine with what's called sensor fusion and AI algorithms. So today, if you had an older device, it's not very accurate. So you're driving, and if there's GPS, right, you use GPS. It works actually pretty good in a clear sky.
Yep.
And so every millisecond, you can monitor GPS. And as you're driving, all of a sudden, you start to lose GPS. You have an algorithm that says, hey, your GPS is fading, whether it's going into a tunnel, whether it's GPS denied, whether it's a barn, whether it's urban canyon. And the algorithm says, hey, weigh the gyro more and less on GPS. And as you completely lose GPS,
it's almost like a smart system.
It's we call it an AI algorithm. We constantly measure. And there's two things. So now, as you're driving, if you completely lose GPS, you can rely 100% on the optical gyro capability combined with acceleration and velocity. And now you can navigate. That's why it's called an inertial navigation system, completely on the optical gyro.
Well, and to tell I want to take a minute to dwell on this because I don't think the importance of this can be understated, especially today. Not just the things you're talking about, Mario, like urban canyons or, I've got lost in downtown Denver because my GPS wouldn't work with all the buildings. Mm-hmm. That was good fun. And that happens to all of us on a daily basis. But when we're talking about beyond visual line of sight, we're talking about military operations and what we've seen, of course, right, on the battlefield in Ukraine. We're seeing it in Israel with the Hamas and now Hezbollah conflict. The prevalent spoofing and jamming that is happening to take these vehicles out, to make them ineffective. They drop out of the sky. I remember there was actually an exercise. This was even before the conflict in the Black Sea. It was U.S. Partner forces. And, the suspicion is Russians did this. They thought they were completely somewhere else on the planet. And that, that's what spoofing is all about. So tell us,
let me explain it, because you hit the right point. So let's call jamming or GPS denied is one case. You lose GPS, your algorithms can tell, hey, I'm losing GPS, whether it's tunnels, urban canyon, or in military conflicts, there's real jamming going on where they jam the airways and you don't get GPS.
Yep.
So we have a solution that's independent of that because, again, we have this little dashboard and we have an algorithm that corrects for any misalignment. And to put into context, we're doing, think about this, 30 to 60 minutes of driving.
Yep.
100 kilometers.
Okay.
I'm going back and forth with metrics. 100 kilometers of distance.
Yep.
With less than 100-meter lateral error, no GPS. So 0.1%. So you can imagine we're going 100 kilometers. And at the end of this, driving around, I'm off by 100 meters because of this technology that's integrated, high-performance optical gyro, algorithms, full system capability that can now be deployed very quickly, 20 minutes in any vehicle. And whether it's agriculture, so in farming, orchards in the fall, the leaves come in and you want to go into, and for spraying, for example, it's a tunnel.
Yep.
In GPS denied capability, there's real jamming and spoofing. So that's jamming. Let's talk about spoofing, because this is where Anello really shines, right? So now spoofing, and you hear these stories of how did this ship end up in this water or that water. Spoofing is someone takes over the satellite signal and essentially cybers it. You cannot tell if it's wrong or not because your system says, oh, I'm getting GPS. It looks pretty good. What do? Because of the system, we can say every millisecond, we have an algorithm that checks where does Anello say you're at compared to GPS, and we compare that real time. And so you can imagine this, if we're driving and Anello says you went 100 meters forward, GPS says I'm in Texas. Hey, something's wrong. You're getting spoofed. Immediately rely on the gyro. And we constantly check this, right? And so this is now a technology that can't be jammed, can't be spoofed, can be scaled to high volume, but also allows for very high performance over extended periods of time in GPS denied or contested environments or spoofing. And this is this dual use. We can apply it to agriculture, construction, farming. We can apply it to military applications or DoD-centric places where you have jamming and spoofing going on. It's not just a military complex, it's affecting everything.
Well,
right?
Hey, Mario, you're preaching the choir here. I mean, I'm very lucky to have been writing for Richard Fisher, for Inside GNSS Magazine, even before I met you. And, one of the things I've been writing about, following, of course, is, the U.S. Department of Transportation's complementary PNT, position navigation timing efforts. Why? Because everything in life, almost in modern society, relies on position navigation timing, from our financial sector, right? To healthcare, to trains, planes, automobiles, you name it. So, this technology that you've pioneered is absolutely amazing. And, this dual use application, it's pretty clear to me what it's all about. Now, you kind of kicked it up a notch this year with this X3. So you have the original SciFog, and then you decide, we can even make this better. Tell us about that journey and what the X3 is all about.
So, we started off with the land vehicle use case because there was a lot of interest, and we have, customers today in the industrial segment across farming and construction, and that is a single axis. Now, what gets exciting? What if I take 3 of those SciFogs and I put them in a little cube? And we can see this in here, and there's 3 of them. There's 3 SciFogs, X, Y, Z. This is a mechanical. There's obviously a board here with the electronics and the CPU. But now think about this. I take this device. Look at this, right? I use my hand,
It's smaller than a Rubik's Cube, like just for context.
Now look at the difference. Same performance, but look at the difference.
Yeah.
Size, weight, area, power, right? It's a fifth the size, fourth the weight, significant reduction in power.
Now,
same performance.
Now, why is this important to have 3? Like, what does the axis of power give us here? Axis
of power. So now remember, in the cars we're saying heading. Now, if I'm 3-axis for things that fly, let's say drones or aerial vehicles, your motion is 3-dimensional.
Yeah.
And so you need to understand your drift. It's an algorithm of all mixing these 3 channels. But as you're moving 3 dimensions, not just air, maritime. What about when you're on the water and you're moving around and there's drift? And so now we've created a capability. And why does small matter? Because for drones, you cannot put this on a drone. It's too much weight, it's too much power, and it's too expensive. We now have a technology that can be applied to drones and or maritime. Now, let me give you the example of what happens here in drones and why it's as important. And we'll use, unfortunately, areas of conflict, but it's real. Drones that fly today, and then we'll talk about the commercial implications in the future.
Yep.
Drones today, like you just said, everything relies on GPS. You have an autopilot that basically flies, and it's relying on GPS. Clear sky, perfect. Yeah. What happens when the drone loses GPS?
Yeah.
It doesn't know what to do. It doesn't. You can't say return to home. You can't say go forward. It sits there. It completely has no sense. And by default, it crashes, or default comes down. And so in areas like Ukraine, numbers that people are losing 10, 20,000 drones a month.
Yeah.
In places in Israel, you cannot fly. There are no fly zones. Well, not only that,
Mario, but you hear these numbers, right? And people think, because they're getting blown out of the sky or whatever. But some of them, like you said, they're just literally dropping out of the sky.
They're not getting blown up. A lot of them are mostly being jammed. So those areas are completely jammed, and it's done by defensive mechanisms. So the world relies on GPS. And so if you jam GPS, now it's these areas of GPS. But if you jam it, you cannot navigate. And it not just affects the drones, it affects everything. So what do we want to do? We basically created a technology. And this is, again, a combination of hardware, software, algorithms, where we take this X3 now, which is 3 SciFogs.
Yep.
We have an algorithm that says we can put this onto a drone. And there's on our website, we see some pictures. We have a hexacopter as one example. We're doing now fixed wing and other vehicles.
Yeah, I think we have a video we'll show here in a sec.
Okay. But now what happens? You're flying, a similar example. I'm flying and I have an algorithm that says, hey, I've lost GPS or I'm losing GPS and I completely lost GPS. we say, don't worry, all is good, rely on Anello, keep flying. Yep. And now we use Anello to navigate through those jammed regions or regions where you don't have GPS.
Yeah.
And we're doing, think about similar thing, 10, 15 kilometers of flying, no sight, no GPS, but we can stay on heading pretty close. And then when you come out of it, either you come out of the GPS, out of the reason, and our algorithm says, hey, GPS looks good, go back to GPS, and we can constantly go back and forth with our algorithm, or we keep flying using Anello. And so what we've done is combination of this technology, because of the size, weight, area, power, combined with the algorithms, have now created capability to navigate whether you have GPS or not. Okay, and
that is huge. That is huge for so many reasons. And I think we use GPS, and I think most people just like, oh yeah, GPS, they know it's a thing. But just to be clear, everybody, if you don't know, GPS is a constellation, a U.S. constellation of 13 satellites, and Europe has their own, Japan has its own, China, Russia, so what we're talking about here is when those signals, they get interrupted for some reason, whether it's, as Mario said, a canopy of trees that block that satellite signal from coming through. Fun fact, Mario, I did a study, I was working with Modal AI, they make a bunch of things, and they have like this interesting horticulture case, because greenhouses are GPS denied environments because the glass deflects.
Sure.
Yeah. So who would have thought about that, right? So the applications for this with drones, whether it's in a greenhouse, in a tunnel, on the battlefield,
even in a building, a concrete building. But similarly, just think about underwater, 6 feet underwater. There's no GPS. So if you look at unmanned vehicles underwater, they don't have GPS either. And so how do you navigate? And so, and then I'll give you the ocean case. Sorry to cut you off, Don. Is like you're in the ocean and you look around, everything looks the same. Cameras don't help you. LiDAR doesn't help you, right? So how do you navigate cost effectively? Is the ability of something like this that you can put into vehicles. And especially if we start moving to attritable things, swarm of things, lots of these things, this is where the volume piece happens. And so, we've now addressed technology, same thing where we can now do land, air, and sea applications across industrial and defense or DoD or government.
Yeah.
Makes sense.
So truly multi-domain dual use technology we're talking about. I want to roll this video because it's pretty cool. I know it focuses on the X3 and it highlights a couple of these use cases. So let's go ahead and roll that. And basically we're seeing the logo here and testing it on the drone, Mario. That's what we're looking at here.
So this is an example. These are one of these jammers. This is an example of something that, these little, they're not very big, some of these jammers where you can just point them at things. But this is an example of a drone. You'll see here that our gyro, our X3 is mounted onto a drone. And this is just an example of us flying simple, right? Hexacopters, quadcopters, and then I'm going to talk about where we go in the future, right? Because it's one thing to talk about contested. This is the X3 on a hexacopter, right?
Got it, yeah.
And again, you see it's the size, weight, area, power matter, right? These drones, a lot of them, they're battery operated. They only go 20, 30 minutes. So if you have a huge device that consumes enough power, you'll take 15 minutes of the flight capability. And this is just us when we were doing initial testing where we fly. And now we actually do, we turn off the GPS, we turn on the GPS. Obviously here, we're located here in Silicon Valley. This is the example where you can fly through a jam region. Typically it crashes, and then with Anello, you can continue to fly through.
Okay.
But we've done testing with the DoD at places like Pentex and NavFest at White Sands, where they do real jamming and spoofing at nighttime, where we actually showed our capability is unjammable, unspoofable. And this is what's getting a lot of people in the government very excited. Not that because it's the concept of fiber optic gyro, it's because SciFog has created technology that you can put into mass amounts of vehicles and not just the high-end systems.
Right.
So very applicable today. The cases that are happening in Ukraine and unfortunately the conflicts in the Middle East and what's going to happen in Taiwan, people are realizing that GPS will be jammed. GPS may not be around. Satellites could get shot down. The base stations on the ground could be distorted. So what do you do without GPS? And now I think we've provided a capability that's cost effective, that works really well, that can be scaled to the mass market.
Yeah.
And so this is today. But think about what this, if you step back from it, and I don't want to put fear in people, but what is this really resolved? To me, it really says, hey, we have to think about this. We may not have GPS all the time.
Yeah.
What happens if there's, and it's what's happening now in Israel and conflict areas, all the areas around there, the GPS jamming, which are done for military reasons, are affecting the civilian use cases.
Yeah.
The civilians can't use their phones because GPS doesn't work.
Yeah.
I've heard a couple of stories.
Mario, we could talk hard. I mean, we could talk about the threat, kind of vector scenarios. I mean, you could have a solar flare, that could just take out a bunch of satellites. I mean, we had a scare recently about this. I don't know that people truly appreciate this. And then, of course, you had the Russians talking about, EMP, right? Electric magnetic pulses, blowing up a satellite and all those little pieces go flying and then they start taking, it's like a huge domino effect. I mean, the scenarios are really endless, honestly. I think planning ahead, and I think that's what the US DOT is thinking about. Like, we got to make sure that we're not wholly dependent on GPS for everything. We need complements. We need backups. We need alternatives. And you're right in there. So I have a question though, Mario, because
sure. Let me add into this, because you said I didn't want to go down that path, but those scenarios you mentioned are real.
Oh.
And I believe that we have a solution that those cases so that we have a navigation solution in case you have a solar flare, in case you have an EMP. It's not just for civilians. Think about this, emergency vehicles, people that need the first responders, National Guard. How do you get around? How do you navigate? We become so dependent on this as a navigation tool. And when you're blind and dark, where do you go?
Or through smoke.
I believe Anello,
all kinds of,
what's that? Yeah, Anello. And, Anello will be at the core of this. And I believe Anello could be at the core of every center because we've created this new technology. Think about the last one, low power. Why can't I put this on every soldier, on every person? You can know where you're navigating any place, anytime, not just vehicles. So this is an evolution over time. And eventually, we'll put it on every phone. It'll be a consumer device today.
Oh man,
this.
When you're
next
talking
generation
about soldiers,
is this, and then it'll be a little chip.
Yeah, like a force tracker kind of thing.
Yeah, and so this is the radicalness, and I do think this is an evolution of technology that will continue to scale. But I'll go back to your question. I just want to follow up on yours. You hit up a good point that it is in time. We should be realistic that these things can happen.
Yeah.
And to me, in Anello, how do we take this technology, and that's to the audience here, I want to take this to the warfighter. I want to take this to the technology. I want to take this out to the consumer. Help us. What are your use cases? What are your applications? Because we want this technology everywhere, and anything we can do to help solve real problems, let us know. Now, you had a question you were going to say.
No, that's really great. So for your SciFog, you put it into the INS. Now, you also have an IMU, and I don't want to end the show. We're getting close to the end of our time together here, Mario, without talking about this other product, your Anello IMU Plus, and explain what that is and how, if at all, it relates to what we've been talking about this whole time with your SciFog.
It's similar thing. So in some places where you already know you don't have GPS, like you're indoor a building, you're in a barn, and you're not GPS or in a parking garage. This is our IMU Plus. So this has the same core technology, CPU, algorithms, obviously optical technology with SciFog, but it doesn't have the GPS chips. So you shrink the device, but this is for rugged. Right now, we're selling this in the robotic applications.
Okay.
People who want rugged robotics. And eventually you'll see this, but these are hardened cases. So in a construction environment, this is hardened. It's not susceptible to weldings going off, dirt, dust. And so now land, air, and sea, but also robotics. And again, if I look at this phase today, robots on the ground, robots moving, Eventually, you can imagine putting into real robots as we shrink this, put it on each arm, putting it on, movable robots that you want accuracy. Your brain and the human being has a very good gyro, a combination of eyes and your.
It's funny you say that until it doesn't, my friend, because there's little tiny, tiny, tiny crystals in your ear that if they get slightly out of whack, you are hosed for days. Not that that has happened to me, because it actually has.
I've had it happen to me once.
It's called vertigo, and it's a living hell.
Vertigo. Not good.
Yeah. But, we don't want that for our robots, right? We don't want that for our drones or our submarines, and certainly not for our ICBMs and other, kind of vehicles that are out there. So, no, this is really awesome stuff. And I've learned so much, including what Anello means in Italian, which I didn't know until this show. So we're getting super, super close to our time together, Mario. Mm-hmm. So let's make sure we covered everything you wanted to talk about first. And then second, tell folks, because you kind of made a plea to everybody like, hey, we want to hear your use cases. We want to know your pain points. We want to work with you. Tell them actually where they can find you and how they can reach you.
So first of all, it's been a long journey, right? We started this crazy idea of building something that didn't exist before. There was no track record, and you had to build your own models, your own simulations, trial and error. Fast forward today, we have not only SciFog, we have existing products that we're shipping, the GNSS INS, the IMU Plus, and the X3. We're shipping that into both industrial and DoD applications. And then we'll continue to evolve that over time, continue to reduce power, reduce the size. The technology's here, it's about taking it out to the mass market. And so while we've explained a few use cases, what are those customer applications? What are your use cases where you need better accuracy for navigation, GPS denied, GPS contested? And, love to hear from you. The website, www.anellophotonics.com. There's an info@anellophotonics.com where you can send in a request. We have our products on there. We have some videos and some spec sheets, but really send us a request. Tell us what your use case is, and we'll put our business development people, and we have field applications engineers. And how do we morph or modify or enable our technology and products to solve your problem? And, some of the things we're talking to customers are coming out with use cases and applications I never would have thought of. Right. And we always think of these high-end defense ones or like farming, construction is obvious, but there's a lot of these other ones. And even now, we'll announce in the future, but we won a contract, with the DoD to build a man-portable concept based on this. So think about this, take the same thing that's in your phone, but now put 3 of these on there, put it in your pocket. Any person can navigate. And a lot of this is for soldiers, right? They come out of a helicopter. It's GPS then extracted to emergency responders going into buildings, smoke, fire, right? And so to me, we've developed this core technology that I think has wonderful applications. And so love to hear from the customers and from users of how can we solve your problems and provide you with GPS denied or GPS contested navigation solutions.
I love that. My brain's spinning. And my question then, my final question to you, Mario, is, are you going to CES again in January?
We'll be there. Please come by. Love to talk to you there. And we'll be announcing something special again. And this one will be more on use cases. Yeah, we'll show you some cool, exciting things.
Okay, awesome. So
we'll see you in Vegas.
Yeah, I saw you at Commercial UAV recently. You guys were there as well, kind of talking to that drone crowd. So really excited to first of all hear this new use case upcoming in January at CES, and then of course continue to follow you. So everybody out there, you've got Mario's information, you've got the Anello website. Reach out, collaborate. That's what this show is about. And really appreciate you. This was super fun. I loved hearing your story, and what you've done here with your team is quite groundbreaking. And so it's been an honor to have this opportunity to share this with our audience. So thank you so much, Mario. And thank you, everybody out there. We appreciate you. We are out here.
Thank you. Pleasure, everybody, and look forward to seeing you or meeting you. Come by CSCS, LinkedIn, website, sign up, get on our mailing distribution list, and we'll see you in Vegas, Don. Take care, everybody. Thank you.